All right.
So we were at this slide last week where we stopped. So what we were studying, basically we covered a few uninformed search algorithms, right? Breadth first search, depth first search. We also covered uniform cost search. And then we talked briefly about greedy search. And we discussed an issue with the greedy search that it would either take you straight to the right goal or it will get you stuck in loops, right? And we looked at traveling Romania issue, and we saw where greedy search can basically cause you problems, even though it tries to, go for the closest possible, like the next, it will only expand that node that is the closest to the goal, right? So it's trying to be greedy and trying to take you the closest to the goal, but it will. So in situations where you have like loops or cycles within your problem, then it actually causes issues. And we said that suppose that you get very close to your destination, but you just end up being in a dead end street. You will just get in the dead end street using the greedy search algorithm, and it will just get you stuck there. Or it will only find basically the path where go towards the direction which is the closest. And we discussed the idea of relaxed problems, and we looked at the simulation, Pac-Man simulation, and said that in Pac-Man scenarios we try to relax the problems, right? We try to find the solutions using relaxed problems, and we will just calculate the Manhattan distance. We'll start with ignoring basically the walls in the Pac-Man scenario and try to find out what is the closest. And if you remember, I'll actually show those slides in just a few moments. So we said that the uniform cost search, basically it looks at the G of n. And does anyone remember what G of n was in the function? It looks at the G of n, which was the additive cost or the backward cost. Wherever we're coming from, we keep adding the cost from where we were coming from, right? And then we look at the next node, which is why UCS or uniform cost basically will start with expanding in every single direction, because it looks at the path cost, right? And then it slowly gets closer and closer and closer to the destination, right? But we wanted to avoid an algorithm. We wanted to design an algorithm that is better and just doesn't go or doesn't expand in every direction in the beginning, even at least in the beginning. We wanted to get better. And then we said that instead of looking at the backward cost, why don't we look at the forward cost, right? And in traveling Romania problem, we said that, well, we assume in a greedy search algorithm that there is an expert, an oracle, someone, a saint, who basically has given you the shortest SLD. Remember the straight line distance. From each city, it will just show you or give you that, okay, here from this city to your next closest city, here's the distance in kilometers or miles, whatever, right? And then we said that instead of looking at the backward cost, we're looking at the forward cost, which is H of n. And what was the forward cost? Well, forward cost is basically the prediction or something that you don't know, right? And we call it heuristic. And the definition of heuristic, as I explained in the last lecture too, it's an educated guess, okay? Or an estimate that someone has provided you. But we said, we covered that the greedy search algorithm also has problems, right? It's just greedy. It will just either take you straight to the goal, or there are cycles in your tree, or where there are loops in your graph, it will actually take you to the wrong goal. It will not be optimal, right? So, and then we said that what should we do to get things, to make things better? We have uniform cost, which is f of n, and that is g of n, f of n equals g of n. And we looked at an example, right? Started with this, and then we said that, okay, initially, by the way, please remember, and let's not forget, because this is part of your programming exercise. Remember, we said we're going to maintain a fringe. And what is the fringe? A fringe is going to be a data structure that you will have to maintain in your Python code. In DFS, it's going to be your stack, right? Or queue. Stack. In DFS, it's going to be a stack. In BFS, in breadth first search, is going to be a queue. In A star search, in uniform class search, and greedy search, it is going to be a priority. Please remember it, because you will have to implement these in your code. Yes. So in depth first search, it's going to be your stack. In breadth first search, it's going to be a queue. And for the rest, UCS, greedy, and A star is going to be a priority. And we'll see what priority queue is very shortly. And so we will have to maintain a fringe, something like this. So you look at S, right? We have S. So we have G of S beginning, because we don't have, this is where we are at. So G of S is 0 at this point, right? Make sense? Because this is where we are. So G of S is 0, and H of S is 6 in this case, right here, right? So this is what the values are. And then from S, we can only just go to A, right? And how do we do that? So we apply basically, G of n, apply UCS first, basically look at the G of n only, and then we apply greedy, and then we see what, each of the techniques have, what issues are associated with each of the techniques. If you look at just G of n, from S to A, the G of A is only 1. If you look at this part, only 1, right? This is what it is. All right, we get to A, and then we look at uniform cost search, right? It looks at the lowest G of n and then makes a move, right? And so now from A, it can go either to B, D, or E. And look at the additive costs. Okay, additive cost from A to B is 2, right? Where did this come from? It's actually additive cost. This plus this. All right, G of 2. And then from A, we can also go to D. And G of D is 4, which is 3 plus 1, 4. This is how we calculated this. And then from A to E is 9, which is 8 plus 1, 9. This is how we calculated. And then from the 3 different options, B, D, and E, it will obviously, UCS will go to B because it has the lowest G, right? You see, G is 2 here, it's 4, and then it's 9. So it will go to B. And then from B, the only place to go is C, right? And it's the G of C is equal to 3. 1 plus 1 plus 1, 3. Now it's actually, it has started going in the opposite direction, and that's where the dead end is. From C, you just cannot go anywhere. You have just gotten stuck in a dead end street. And UCS basically has caused you a problem. Now, with greedy search, if you look at greedy search, we're looking at H of n, right? Basically the H values. Now let's forget G of n for a moment, because we're looking at only the greedy search. Somebody has given us the heuristic and these values, and we're looking at that. So from S, obviously, is going to go to A because there's no other place to go, right? And from A, it can either go to B, D, or E. And now look at the H values. From A to B, the H value is 6, right? From A to B, the H value is 6. From A to D, the H value is 2. And from A to E, the H value is 1. Where will it go? A to E, obviously, right? So it will go in this direction. H1. And then from E, it can only go to D. And then from D, it can go to G, to the goal state. But the problem is, we only looked at the future cost. We haven't seen what the arc cost is, how much it is going to cost, or how far the node E is, or on this route, how much traffic it is, or if there are any lanes that are closed. If it is the time when there is a, when the places get closed, like schools are closed, and there is a lot of pedestrians crossing or something. So it's basically ignoring all of that. The algorithm only is looking at the heuristic. Well, that's the issue, right? Because is this optimal? No, right? It's not the best solution. The idea was for A star, does anyone remember what the idea was? Taking the G of n and H of n and doing what with it? Adding them together. Exactly. What we then do is we come up with the A star set. And once again, please remember, the most amount of effort and work, research and development work that is done in A star search is basically coming up with this heuristic or updating the heuristic dynamically. All right. So A star basically has been used in many different fields, but one of the most common and famous field is basically the pathfinding problems. All right. Ronald. Yes. So that's what Google does, or that's what researchers basically do, is that, instead of just making it a static algorithm, basically it updates, in real time. It updates dynamically. It keeps getting the useful information, and it keeps updating the heuristic. What do you mean by non-useful information? That's the main question. Once again, I would say that's part of the research, and would see, how people use basically navigation, right? What is the useful? What do we even mean by useful information? In pathfinding, what are the factors that you include? Weather, traffic, right? Avoiding freeways, not avoiding freeways, avoiding roads that have too many traffic lights. So this is all useful information. So when we do the goal formulation and problem formulation, the information that is included for A star to even do this, to apply the search algorithm, it's a useful information. Otherwise, your goal formulation is basically not accurate. Okay. Yes. We'll study that soon. All right. One very, very important in all your algorithms that you're going to implement. The question, when should your algorithm terminate? Okay, so you have a fringe. You have a fringe that is a data structure. You're pushing nodes in it, okay? You're pushing values in, and you're popping them out, right? You're popping them out. When you push them in, then that means you're creating a tree. You're creating the entire tree. When you're popping the values out of your fringe or data structure, then that means you're expanding those nodes, expanding the children of those nodes. So whenever I say pop that out, pop a node out of your data structure, then that means you're expanding its children. Okay, for each of the children of the current node where I am at. All right. So the question is, when should we terminate the algorithm? Should we terminate the algorithm when we have the goal and we say, when we push it in, and then we say, okay, we found the goal, we pushed it in, perfect, fine, stop it, great, we declare victory. Or we just ignore it, we say it's a goal state, but still push it in. But the next time when we pop that node out of the priority queue or the queue, and when we pop it, should we declare the victory? So this is a very, very important question. Now look at this. So let's just even try to solve it. Okay. Now we're gonna have a fringe, right? Now we have S, right? We can basically we start with S. So G of S is 0 at this moment, right? So from, remember this formula. That's A star, right? That's A star, sorry. So now from S, we can either go to A or we can go to B, right? From S, we can go to A or we can go to B. Now watch what happens. From S to A, okay, what is the F of N? What is G of N from S to A? 2. Okay, and what is the what is H of N? 2. This is 4, right? But from S to B, what is G of S to B? G of B? 2. And what is H of B? 1. All right. So look at the formula. F of N equals G of N plus H of N. So from S to A, the G of A is 2 plus H of A is 2, which is 4. And then from S to B, the G of B is 2 plus H of B is 1. Oh, okay. Okay. So H are the values that are right next to the node, right next to our, future node where we're going to expand. So obviously, what we're going to do is we're going to remove this, ignore, yes. That's where we are at. So we will worry about H of S if we were somewhere before S, okay? Because H is the future cost, right? Forward cost. So when we are at S, we're not going to worry about H of S. Okay, all right. Yeah, forward cost. We will say forward cost. H is basically an estimate, which is a future, estimate. Okay. G of N. That's the backward cost. Yeah. Okay. So that means we're going to pick S to B, right? To be here. And then from S to B, we can go to G, right? So what is, sorry? Okay. And then the G of G, what is G of G in here? 5, not 3. Additive cost. Remember, additive cost. 5 plus, what is H of G? 0. This is 5. So right now, let's say we are going to just declare victory because we have reached the goal state. Right? Is everything okay with it, what we have done? Why? SAG is optimal. So as soon as we enqueued the goal, meaning pushed it in, we declared the victory, and that's where we have made a mistake, right? Because now suppose that if we didn't declare a victory here, suppose that we did not, and we went back, so it was something like this, right? So from S, we can go to A, and then we can go to B, and then we can go to G, right? So we have expanded this path. And as soon as we pushed it in, we declared victory. But now let's see. We looked at the cost right here from SBG, but we waited. And we didn't finish. And then we said that, okay, how about if we explore this path, and see what happens? Then from S to A basically was 4, right? It was 4. And then from S to A to G, what is a G of G from A? 4, right? And then H of G is 4. This is the optimal path, right? So then what we do is we explore this one too, and then this one too, and then we look at the lowest cost. Here we dequeued this one because this one is with the lowest cost. So the idea basically is only stop when we dequeue the goal, not enqueue the goal. So in your code, please remember, don't declare or don't put an if condition when you have pushed something in your data structure. When you pop out, after you pop something out, then put an if condition. Yes.
So then is the reason why when you found the optimal path first, because the district wasn't accurate?
Heuristic wasn't,
Because it should
I
be,
wouldn't say, yeah, I wouldn't say it's accurate, because accurate is basically it's a composite. It's a composite problem. That's what we're gonna cover today for the rest of the lecture today. It has to be admissible and it has to be consistent. And we will study how we can make our heuristic admissible and consistent to make sure that ASR is optimal. If it is not admissible, if the heuristic is not admissible or is inconsistent, your ASR is not going to be optimal. We're going to face problems. Nathan, sorry. What do we use to set the priority? So the priority in this entire problem is our lowest cost. What is the lowest additive cost that we have? We have to find, basically, we have to find a node within our entire stack or queue that has the lowest cost. That has the lowest additive cost. So we're going to see something like this, you know. So we keep moving from S to A, we get the cost. From S to A to B, then we get the additive cost. We add the cost in our code, right? And then we from S to A to B to C somewhere else, we add the cost, and then we say, for this path, what is the cost? The additive, complete additive cost. For probably another potential path, we go to C, not from S to A to B to C, or maybe S, A, B, C. We look at that cost, and we will follow the path that has the lowest minimum.
So G event sets a priority.
Right.
G event.
Yes. Yes, and we will also look at an example. Right.
So to DQ holds.
No, DQ is, so what you do is you push something in your data structure and you're creating an entire tree, right? And then at each node, when we get to this, right, we say, we pop this in out of our data structure, we pop this out, and then after we pop this out, we saw what are its children, A and B. So that means we have expanded it. We've expanded it, right? That's where we're popping it out. That's dequeuing. That's what dequeuing means. We pop a node out of your data structure. So you have a stack, right? You create a stack. How do you play with stack? So you insert elements in the stack by using push, like stack.push, and then you insert an element. Now you want to get an element out of the stack. You say stack.pop. And stack.pop is a built-in function that basically takes the top or the last inserted element from the stack. That's the pop. You know, it will be something like this. Your fringe name dot push, and this is basically node, and then fringe dot pop. This is what you're going to do in your Python code. As soon as you pop, you say, okay, here it is. And then after this, you say, okay, this is my node, new node, right? And I say, if n is, if n dot is goal state. If it is a goal state, come on, please. Then declare victory here. Something like this. You will do something like this, okay? All right, so I'll show you that. I'll show you. Okay. Do you guys see an issue with this graph? First of all, which path will it choose? ASR. Bottom one. Well, but is there an issue? Do you guys see an issue with this? Bottom one is not optimal because you know why? Do you guys see any problem why it is the bottom one is not optimal? So you see H equals 6 for A, H is equal to 6. Then that means if it was a traveling Romania problem, then the person or the expert who gave you the traveling Romania, map with the straight line distance are wrong. That means your H equals 6 for A basically is the one that is causing problem for you. Your heuristic basically is not consistent or is not admissible, right? Because there might be a situation when your educated guess basically is not correct. It's probably not correct. So if we are going to look at this issue, once again, we're going to have a fringe. We are at S, and from S to A, we have G of A, which is 1, and then we have H of A, which is 6, this is 7, and we have S to G. G of G is 5, right? And H of G is 0. Obviously, it's going to pick this path. But the problem is, this thing, the guy who gave you the map or educated guess sucks. He's a sucker. Okay? They didn't give you the correct information, which means here, the actual bad goal cost, has to be less than the estimated, or is less than the estimated good goal cost. That's the problem. So your H, your heuristic, might not be consistent or might not be admissible. It might not be correct. Make sense? And we will see how or what. So or what do we mean by inadmissible heuristic and inconsistent heuristic, and how we can correct it. That's the most important work that A* goes through. A* has to have Ronald.
So it's not actually A to G. What you're saying?
The cost. No, we're estimating. We're having a bad estimate. The actual cost from going, the actual cost of going from S to A is less than what we are estimating. So somebody has given you a bad estimate.
Okay, so these numbers.
H is wrong. H is wrong in this case, and we will see how we will correct H.
Oh,
So we need estimates to always be less than the actual cost. Our estimate has to be, we have to underestimate. If we overestimate, it's going to be a problem. Okay? So we have to say that our estimate will have to be less than the actual cost. Okay, what do we mean by what do we mean by our admissible heuristic? All right, remember we said, sorry? Yes, it has to be less than the actual. So remember we covered an example. We said that in our problem solving using search algorithms or whatever algorithm, because our world is absurdly complex, we have to relax our problems, or we have to do the goal formulation first. We have to hide the unnecessary details, right, in order to solve a problem, in order to actually do formulate a goal, right? And that's what we studied in software engineering too. In Pacman scenario, we said that one way to start solving the problem is to basically avoid the walls and then just look at the Manhattan distance and then see what is basically the closest. What is the closest next step that needs to be taken, right? So in our admissible heuristic, all what we will have to see is that a heuristic H is admissible or optimistic if the estimate, this is our estimate, and this is the true cost that we have. Okay, so our estimate has to be less than or equal to the actual cost. Okay, so we will see with an example how we will make sure that our estimate has to be less than or equal to the actual true cost that we have. Okay, so we'll look at it using an example. So once again, admissible heuristic. Admissible heuristic is what is mostly involved in the research and development based on A-star search. Okay, we'll have to make sure that our heuristic basically is admissible. So for admissible heuristic, the optimality of, remember, we're looking at tree search for now. We haven't gotten to a point where we have made a transition from tree search to graph search algorithm. There's only one very important element in graph search that differentiates basically differentiates it from the tree search algorithm. We will see that. I'm going to have to skip just a few slides here and get to the examples of how we can make the heuristic admissible and consistent. If we have time, we'll come back to prove how A-star search basically is optimal by expanding the nodes and seeing like, okay, if there is a goal that is an optimal goal, and then if there is a suboptimal goal, how we will make sure that A-star will always select the one that is an optimal goal using tree search. If we don't have time anymore, just because we had a day off on Monday, if we don't, then I have about 9 to 10 minutes video that is recorded for the optimality part, and I will upload it so that you can take a look at it. But let's get to the important part first. Optimality. Here, I'm basically proving. This is basically just a proof of how we make sure that the A-star search algorithm is optimal. Okay, so let's just play a few algorithms just for us to remember how sorry. Look at A-star. Okay, A-star did much better, much better. Remember, we said that instead of UCS where we had the start, right? And then we had the goal. And remember, UCS basically would expand something like this. And then for A-star, our goal basically is to initially just expand a little bit like this, then get closer and closer and closer to the goal. And our goal basically is to expand the least number of possible nodes that are away from the goal using A-star. This is how we will make it optimal, and we will make it complete. Okay, Ronald. Where the goal point is.
Is it like seeing behind, or is it like see where?
No, we're talking about f of n equals g of n plus h of n. So h of n tells us where about the goal is. Okay, h of n, because h of n is telling us which next node is getting us closer to the goal, or it is getting us farther from the goal. Okay, so heuristic basically tells us where the goal is. And then there is a backward cost too. That we said that, okay, we looked at the future, right? And now we've also traversed a path, in our past, and we also look at that cost. And we just basically combine both future and the past. So the future, the heuristic tells us where our goal is in the tree. Okay?
And that's already
Yeah, the heuristic is already given to you. That's what I mentioned. Okay.
Oh.
All right. So we said, I think let me just play this quickly, and then let's get to the actual problem. Okay. Do you guys remember that when we talked about the greedy search, and if we said that by having relaxed problems, the greedy search based on this Manhattan distance, the greedy search was basically making this part hotter, like more red, this part more red, this part more red, and this part more red. Like this, right? But is this an optimal path? It's not. You know why? And you know why greedy search was finding that? Because all what greedy search was doing was using a relaxed problem, using the Manhattan distance, it was just getting closer, ignoring the walls, and it was just pretending that I'm getting closer and closer and closer to the goal, but ignoring the walls. In greedy search, the algorithm did not tell the Pacman agent that even though, so in greedy search, basically you went this way, right? The Pacman agent went this way, and h of n basically decreased, right? Okay, h of n decreased. What greedy search does not tell this algorithm, or does not tell the Pacman agent, that even though if you go away about 2 steps, even though if you go, away from the goal about 2 steps, but there is another goal situation or goal state that will be much better for you in the future. Okay, for you in the future. So we're only looking at just the heuristic. That's the greedy search. That's the problem with the greedy search. What we have to do is we will also have to see what g of n is, which is why we combine g of n plus h of n. And this is why, even though this is slightly harder, but A star search was able to find a path here too. And now we have to make sure that this path is basically find out that this path is the most optimal by using h that is admissible and that is consistent. Okay, so let's get ready. But before I got ready, remember I showed you the path from Arad to Bucharest, and it showed something like this, right? If you guys remember, there was a node here, there was a node here, there was a node here, here probably, and something like this, and then we had this. Or something like this, right? But I said in actuality, it doesn't look like that at all. This is how complicated, the map from Arad to Bucharest is. So Bucharest is right here. I don't know if you guys can see it all the way at the bottom right. And Arad is right there. And it's actually much more complicated. A star actually has found use in several different fields: video games, pathing, routing problems, resource planning problems, robotic motion planning, language analysis. And we will actually see some of those examples in our coming weeks. We will see where A star has played a tremendous role, in which fields. Okay. So, I have another video. Let's see. Oh, I think it's a algorithm guess for you guys. So which algorithm would you think this would be? Remember, this is the shallow water, and this might have a cost of, let's say, 5, and this might have a cost of 2. Which one do you think this algorithm was? Breath first. You know why? Exactly. It didn't care if it was shallow water or if it was deep water. Right? You see? It will just expand in every direction. Every direction is not caring about where the shallow water is, where the deep water is, right? What do you think is this algorithm? UCS, right? How about this? A star will not go through the deep water. It's greedy. Greedy is telling you just go through the deep water too. It's just all what it's looking at is it's finding out the next node that is closer to the goal. That is it. Okay. How about How about this? Depth for search. Exactly. Left, left. How about this? That's A star. All right. Okay. So let's get to our main point now. I think we played enough. Let me get to this slide. All right. I think we have discussed a little bit that in tree search, we have a problem basically of repeated states. Remember where we had loops in our graphs, and if we just create a search tree from those loops, it will never end. The space, basically the storage space of those loops of those graphs, because of the repeated states, it would just take us to infinity, right? So the idea basically to have, we still have the search tree, but the idea to avoid basically the repeated states, avoid the repeated states is to just not bother expanding a state that has already been expanded. Okay, or not bother a node that has already been visited before. Make sense? So the idea basically is to, even still we have the graph, right? We have the graph that is okay. We're going to talk about the, how basically the graph will still have loops, but we will be able to avoid, or like not avoid. We will put basically a check on the nodes, on each node which is visited, and we will just simply not visit it again. So what is the idea behind that? So let's say all right. So remember we had the graph search of the 12 nodes that we had last week, right? And we applied breadth first search, right? We said that from S, we can go to D, E, or P. And then, from D, we'll go basically from B, C, D, then we go to H, R, then we go to Q, and then we will just expand this, right? But the idea, basically the problem is, you see here, E, this is E, right? We have expanded E. But there is an E right here too. From BFS perspective, don't you think this is better? Right? But if we have A star, if we have H of n and G of n, how would you know that this is better? This has the least cost and this has the higher cost. We don't, right? And that's the problem. In A star, we will have to decide, when, or is it a better idea to choose this one and drop this one? Or in some situations, choose this one and drop this one? Nathan. Right. We can look at the backward cost using UCS. Basically, UCS will find that. But the problem is, with UCS, we have seen that it still goes in all possible directions at the beginning to expand. We want to reduce the number of nodes that need to be expanded, which is why we came to the solution with A star, right? So what we did was, so we had UCS that basically, looks at the G of n, but initially because it expands in all possible directions and then slowly gets closer and closer to the destination, it actually is relatively slower. Then we have greedy that is much faster, because all what it cares about is the H of n. But there is an issue with each of these algorithms. What we are trying to do is, we are stacking them to on top of each other, because this is h of n and this is g of n, and we are stacking them together on top of each other and coming up with a solution g of n plus h of n. But here, okay, with g of n, we will find out, okay, only g of n, okay, this e is better. But what if we have the heuristic? Now, how will we find out that this e is better to expand instead of this? Or this one is better than this? That's what, takes us to the discussion about basically how to make sure that the what is it called? The heuristic is admissible or consistent. That brings us to the discussion. But the first idea is in graph search, how do we find the idea is never expand a state twice. So remember we had a fringe, right? So we had S, let's say A, D, E, P, blah, 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 blah. And somewhere in the fringe, we have the goal state, right? Now all what we're doing is we are doing fringe dot push, fringe dot pop, etc., etc. From the code perspective, can you think of how we can implement something that we will find out that we haven't expanded, or we haven't expanded the current node that where we are at, or we have already expanded it, or we have already visited this node? Maintain an array. Maintain a separate array. So if you pop something out of this fringe, just put it in another, I would not say an array at this moment for now. Maintain it in another data structure. We can say, all right, we can call it our visited nodes. Sorry, visited nodes. In array, in a list, we can, but there's a problem with the list. Slight problem. Every time you see that, it has been visited or not visited, it may get repeated values. So to avoid space issues, we can use a set that has unique values. So we can have a, come on. So how to implement this? You have tree search, and then we have set of expanded states. That is closed. That is just a closed set. So every time if you're going to expand a node, something, check if you have expanded it or not. And you check the closed set. That is it. Okay. So you maintain another, another data structure, which is a closed set. Okay. Store the closed list as a set, not a list. Okay. Can graph search wreck completeness? Graph search. If there is a solution in the graph, out of all the examples that we have covered so far, we have reached a goal state, right? Forget about the optimality. We have reached the goal state, even using A** search or the graph search, right? So actually the answer is it doesn't wreck the completeness. Nathan.
So you visited, say, but you never expand that before you expanded it.
So if we have expanded E, then that means it's basically the same E that we have somewhere down in the graph too. So the E will appear here and E will appear there too. So suppose that A* actually went on to the deeper one, but it still has gotten to the goal state. So it will not wreck the completeness. But the main question is, how about optimality? Will it wreck the optimality? Will it? Yes, it will. And we will see how it will actually wreck the optimality. Just look at this example. Okay. Let's just work on this example just for about 5 minutes and see how interesting it is and how this basically causes a problem. Now we are with graph search. Remember, we are with the graph search. If we are visiting one node, we're not visiting again. We're not visiting the same node again. So what do we do? First of all, just to be careful and safe, we're going to have a fringe and we're going to have a closed set. Sounds good? So we start with S, right? We start with S and we expand it. From S, we can go to either A or B. I'll just write A, like S to A and S to B, right? So we have expanded S, correct? We're going to put S in the closed set. We're going to put S in the closed set. Sounds good? So from S, we can either go to A or B. All right? We can either go to A or B. All right. So, yeah, I was missing the edge. It was in the animation. Okay, we can go to A or B. So what is the f of n? Remember, this is f of n equals g of n plus h of n. We're going to apply this. So what is g of A? 1. And what is h of A? 4. This is 5. How about g of B? And how about h of B? It is 2, right? Altogether. All right. So that means we will get to B. All right. Okay. So we'll get to B. We will expand B. So from B, we can go to C, right? And we put B in our expanded, in our closed list, closed set. All right. What is f of n at C? SBC, which is g of n is equal to 3, and then h of C is 1, right? Which is this one. So this is 4. Great. So from C, we're here. We can only go to G from here. Great. We have put C in the closed set, and we do S, B, C, G. Right? And what is the f of n? Here, S, B, C, G. 3, C, 3 plus 2 plus 1, which is 6. And plus h of g, which is 0, which is 6. Does everything look good to you? No, right? What is the issue? Look at this part. SACG, 3 plus 1 plus 1, 5. Right? Sorry? You can no longer expand C. So you see here, so when we were here, okay, we expanded C. We expanded C, right? And we put that in the closed set. And when we got here, we have 6. And here we have 5. We have 5, right? So we get from S to A to C, and f of n equals S to A to C. So 2 plus 1, right? Which is 3. So this is 2, and then plus 1, 3. Now we have a comparison between this and this. Remember, because we are only declaring victory when we DQ the goal. All right. So 3 is definitely better, but the problem is we already have C in the closed set. So we cannot expand this one, and we will go this way, which is not optimal. That's the problem with the graph search. Okay. Oh, I already had that in the slide. Okay. So let's talk about the consistency. The consistency is that in order to, so remember, we already talked about the admissibility. Admissibility was 0 less than or equal to h of n, h star n. This was the true cost, and this was the estimate. And the estimate will have to be less than or equal to less than the actual cost, right? Okay, that makes sense. Now let's talk about the consistency. By the way, consistency implies admissibility. What do we mean by that? An admissible heuristic does not have to be consistent. It doesn't mean that it is also consistent. But if it's a heuristic that is consistent, then that means it's also admissible. Okay, so we have that equation, and then we will have another equation, which is admissibility. We have talked about it already, right? Heuristic cost is less than or equal to the actual cost. Make sense? So far, so good? H of A, which is basically H of A, okay, should be less than or equal to the actual cost from A to go. Okay, that means we have something like this. And if we have, another path, another way from A to B and then to G, which is what we have just looked at in the previous slide, right? So a consistency, we look at the arc cost. Right now we looked at the H of n, right? H of n only, or H of A and H of B. Now we are actually looking at the arc costs too, to make sure that it is consistent too. Consistent as well as admissible. So that means the arc consistency tells us this equation. Just gives us this equation. H of A minus H of B has to be less than or equal to the cost from A to B. Okay, meaning, look, here, what is H of A? 4. What is H of B? 1. And what is the cost of from A to B? 1. Is this true? No, we have found a violation. That's the violation. It is not a consistent. This is where A star works the most. It actually adjusts these, adjusts the heuristics, several times, applies the algorithm to make sure that this heuristic is correct. So that means either this is incorrect or this is incorrect. It would have been correct if it was something like this, if this was 3, or if H of A was 2. Then it was correct. Okay, so we look at the H of n, which is the admissibility, and then we look at the consistency. H of A minus H of B, it has to be less than or equal to the cost from A to B. So let's just do it with an example. We have 10 minutes, and I promise you it's a pretty interesting example. Optimality, summary. Let me just create a new slide here. And then let's go over it very quickly, okay? And then we'll be done. Where am I supposed to do this? Okay, so let's create the slide here. And let me just bring the graph that we have. Okay, so we have S. Let's go with this one. A, B, C, and G. Okay, so this is S, A, B, C, G. So we have a path like this, a path like this, like this. Some people know this issue. C to G, and this is B. So we have G of n, right? We have R costs. So we have 1, let's say 1, 4, 2, 5, 2, 3, and 12. Let's suppose that we have this as g of n. And let's also suppose that we also have a heuristic function. Let's just assume that it's not Slale, it's state, because if I just put another dot on it, it will disappear. And then this is, oh, but it will disappear. This is H, okay? So we have S, A, B, C, and G, right? So for this, let's say from H of S is 7, H of A is 6, H of B is 2, and H of C is 1, and H of G is 0. Now let's look at, remember, we're going to cover the example based on the admissible and consistent heuristic, right? And our idea is to find the lowest cost path, right? Which is the highest priority, which is our highest priority, right? So far, so good. We'll have to find the lowest cost or the highest priority. So let's start, basically, let me change the color. And let's create a fringe or closed set. So we already have a fringe. And we're going to push and pop, and then we have the closed set. So we have S, right? We start with S. From S, we can go to A, right? Or we can go to B, right? So from S to A, so we put S in the closed set, right? Now, from S to A, what is the G of n and H of n? 1 plus 6, right? This is 7. Remember, here, H of S was 0, right? G of S was 0 because we are already at the start state. And H of S is 7. So to get the G of n, all what you have to do is get the G from the parent, from the tree, and then add it to the next cost that you have. Something like this. Look, we got basically the G from the parent plus the cost from S to A, and we got the G of n. And then we have the H of n, okay? So from S to B, we have the G of n from the parent. Come on. G of n from the parent, and the cost, which is 4 plus H of B is 6, right? Where do you think will it go? Which path will it expand? Okay. So from B, it can only go to C. Okay, what's the F of n here? From B to C. So 4 plus 2, right? So that's our G of n. Ah, come on. G of n plus H of n. What is H of C? 1. This is 7, right? We put B in the closed set. So we have 7 here, we have 7 here. In case of the tiebreaker, we actually, the typical solution is we go with the alphabetical order. And so according to the alphabetical order, where should we go? Which one we should expand? S to A, right? So from A, we can either go to S to A to B, or S to A to C, or and S to A to G, right? So from S to A to B, what is F of n? What is the F of n? A to B. So we get the G of n from the parent plus from S to A to B, which is 2, this one, right? So this is B, by the way. And then G of B is 2. What is it? 5? SAC, what is SAC? 1 plus 5 is 6. 6 plus 1, which is 7. And then SAG, 13 plus 0, right? Because h of g is 0. So where will it go? From 5, 7, 13, and 7. SAB, okay. So here we also explored C, right? So it will go to where? SBCG, right? So it will go to SBCG. You know why it didn't go this way? B was already expanded. Okay, so for SBCG, can you quickly tell me what the what's the f of n? 9, right? So here we already expanded C. Can we expand this? No. Can we expand this? No. We can only look at this and this, and we will expand this, right? We will DQ and we say, we have declared victory. Is this optimal? Is it optimal? You know why it is not optimal? Can you find anywhere else that has the path that is less than 9? Path cost. SABCG. Look, 3 plus 2 plus 2 plus 1, which is 8. You know why? You know why we have faced this problem? Exactly. So let me just have another. Another slide, and let's go with the same thing. So we had S, A, B, C, G. This was 12, this was 1, this was 5, this was 2, this was 4, this was 2, and this was 3. And we had our heuristic. Boy, S, A, okay, I'll put it here. S, A, B, C, G, right? This was 7, 6, 2, 1, 0. Right? Let me just go back to the previous slide for just one moment to show you where the problem is. So we actually found, we found a problem here, right? Let me change the ink. We found the problem here, right? We weren't able to expand it. So let's check. Remember, h of A minus h of B has to be less than or equal to the cost from A to B, right? Let's put this formula. So we have A and B, right? So h of A, what is h of A? 6. And what is h of B? 2. And what is the cost from A to B? 2. Uh-oh, we found a violation, right? We found a violation. So how can we correct it? Let's change h of A from 6 to 4. No, let's change h of B from 6 to 4. 6, 4, right? All right, great. But we have to check also from B to C, right? Because there is a path from B to C. Let's check h of B minus h of C is less than the C cost from B to C. H of B is what? 4 now. And h of C is what? 1. And is it less than or equal to the cost? No. All right. Let's change h of C from 1 to 2. Right? Let's try with this one. So now this should be 4 and this should be 2. And let's start with this one, close set, S. Okay, from S, we can go to A, we can go to B, right? So from this f of n from S to A is S to A, 1 plus 6, right? 1 plus 6, that is 7, correct? And then S to B, 4 plus 4. That's 8. Where will I go now? A. From S to A, we can go to B, SAC, SAG, right? These 3 nodes. From the graph, we can go to these 3 nodes, right? SAB, what is f of n from SAB? So we get the, we get the g of n from the parent, plus from A to B, 2, plus h of B, which is 4. This is 7, right? How about SAC? So 1 plus 5, 6, right? And then h of C, 2. This is 8. How about SAG? 1 plus 12, 13, plus 0. So where will it go now? We have 7, we have 8, we have 13, and we have 8. It's going to go to B. So we already expanded A, and we will expand B. So from B, it can go to SABC, right? And f of n from SABC, what is it? So look, get the g of n from the parent, 3, plus B. Wait, SABC, 1, 2, 3, 3 plus 2, 5, right? This is g of n plus, what is h of C? 2, 7, right? We've got the value 7. Where will it go? So we have 7 unexpected. So we will put B, right here. So we have 7, we have 8, we have 13, we have 8. Which one will extend? C, right? So we will put C, and then from C we have SABCG. From SABCG, so we will get the cost basically, which is 5, right? 5 from the parent, and then we will say 5 plus 3, 8, right? 5 plus 3, 8, and we have the h of G, which is 0. This is 8. Now we have 8, we have 8, we have 13, and we have 8. It's a tiebreaker. It will go with the alphabetical order, which is SABCG. So now it will expand G. It will get the G. As soon as we dequeue the node, we say it's a goal, and we just stop, and we declare victory. Is this optimal now? Who says no? If you think it's not optimal, can you find another path that is sure as path? No. That's the closest you'll be able to find. So see, that's where the most research is done in A*. You have to make sure that your heuristic is admissible and your heuristic is consistent. And that's where it actually continues doing the updates and continues updating the heuristic based on live traffic, based on the historical data. Google does that all the time. That's why during the event, it actually tells you that, oh, a faster round has been found on live information. That's where it updates the heuristic most of the times. By the way, UCS is a special case of A*. You know how? UCS basically looks at G of n, right? Greedy looks at H of n. A* looks at G of n plus H of n. What if we set h of n equals 0 for all the nodes? Then UCS becomes a special case of A star, right? UCS basically is the special case of A star. Remember, A star is only optimal if the heuristic is consistent, not admissible. Remember, consistency implies admissibility. A heuristic is, if it is consistent, then that means it's also admissible. If it is admissible, it does not mean that it is also consistent. Okay, so A star is only optimal if the heuristic is consistent, not admissible. You have to make sure that it is both admissible and consistent. All right, A star is optimal, and the key in A star search algorithm is basically the heuristic design. That's the key. So this is what you will basically be looking at. Remember, you will say you have in the code, you will do something like this. My XY positions is your stack, okay? Not XY. I would say, I would call my data structure as fringe, and this one, you will do something like this. While true, that's the Python code that I'm writing for you, okay? If fringe is empty, then return failure, blah, blah, blah. Node remove, you will say fringe.pop, and you say, this is new node. And then say if node.xy or position is, no, .xy, is it goal state? If it is goal, then break. Otherwise, for each xy dot children, blah, 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 if xy dot current child, basically if the current child is not in visible nodes, visited, not visible, visited, then do something. Otherwise, just, avoid. So I'm actually writing the code for you. That is part of your homework. All right, take a screenshot. If you forget, then I'm afraid you will have to ask me several times on Slack. Okay. Oh, I have to leave the class because I think there are other people who are. By the way, next week, we're going to cover adversarial search algorithms. I will also upload the annotated slides. Okay. You too.